All right, let's do it. All right, so about a week ago, a YouTuber by the name of JTolan Media put out a video where he's basically showing off his new infrared lens kit. Pretty impressive sort of stuff, actually. Very clear images. Tends to get rid of all the atmospheric crap. So you can see these mountains in the background. This mountain back here is Mount San Jacinto. It is 3,302 meters high and about 188 kilometers away. But I just want to address one thing that he said in the description here. He claims that the mountain should not be visible because of the foreground hills. So basically because of perspective, something small in the foreground can block something large in the background. And he says, I think the most prominent are about 20 miles out of about 400 feet height. So I thought I'd check that out. He gave his observer location in latitude, longitude, which I have plotted in Google Earth, and it's near Malibu, just northwest of LA. And then I drew a line from that observer location off to the mountain. And once you draw a line in Google Earth, then you can then right click on the line and plot a elevation profile. And that basically shows you the elevation from the observer location all the way up to the mountain. As you can see, the mountain up here is about 3,300 meters tall. Right. So I want to test his claim about whether mountains in the foreground should be able to be seen or whether they should be obstructing the mountain in the background. So I'm going to use a Cartesian plane coordinate system again, and I've drawn the observer here at Malibu and the mountain up here. And this line of sight is just a line equation in the form y equals mx plus b, so MO for observer. And what we want to do is for every point along this arc here is work out how tall something has to be for it to entirely obstruct the mountain in the background. So we really want to find out this height for every point along the line. And the way I've done that is basically for every kilometer, we know how far the arc length is, therefore we know what this angle here, and we have another line equation for this long black line, and this long black line doesn't have the plus b, or the intercept, on the end, because it always goes through the origin at x equals 0, y equals 0. So I won't really go through the maths in this one. I mean, we've got our observer here at 46 meters or 150 feet, he said. The target mountain, San Jacinto, at 3,302 meters. And what this table does here is it plots each kilometer. So at 1 kilometer, if you have an obstruction that is 49 meters above sea level, then it will block the mountain. At 10 kilometers, that obstruction needs to be 78 meters above sea level. And at 20 kilometers, it needs to be 126 meters above sea level. So I plotted those two columns, the distance and the height, into an Excel chart, and then overlaid that chart onto the elevation profile. So if I fade it in, you'll see that none of the peaks in the elevation profile get anywhere near that required height to block out the mountain. So that claim of his is clearly false. But he also made another claim late in the video, and that relates to the overall height of San Jacinto. So as I said, it's 3,302 meters tall, and 188 kilometers away. So he is correct in that it's almost 18 milliradians, which is a fairly uncommon angular measurement, but it's correct. So the angular height of Mount San Jacinto is about 17.5, and each one of these levels is half a milliradian. But the way he did this scale was basically by looking at this building here, which is the Meridian Hotel in Santa Monica, and he claims that with the resolution of his new camera, that he can see individual levels, and he has used a bunch of those levels to come up with a scale. And that's a pretty bad way to come up with a scale, because if you take your scale against something very small in the photo, then any errors, so even errors like 1 pixel as opposed to the next pixel, are magnified in that scale. So I guess we'll have to show how bad that scale is. So LA is one of those built-up areas where Google Earth has very high-resolution elevation data. So this is the Le Méridien Santa Monica Hotel, and the level of this roof of the hotel is 65 meters. The elevation up the hill on the street is 31 meters, and down the hill it's 26 meters above sea level. So the building itself is anywhere between 34 and 39 meters tall. We'll go somewhere in the middle at 37 meters. So a 37 meter building at 20.24 kilometers from the observer gives an angular size of 0.1 blah 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 degrees, or in his preferred unit 1.83 millirads. Right, so on his scale, if we have 1.83 millirads and each of these levels is half a millirad, then we'll have 3.66, or 3 2/3 of these little levels. So let's just count. 1, 2, 3, and almost 4. And as you can see, his scale for a 37 meter tall building is way off. The actual base of that building is way below that. I think the base of the building is around here. So this white building here is about 800 meters from Le Méridien. So their bases are relatively close. So if I think the base of that building is around here, then that scale needs to change, because now this distance here is now 1.83 millirads. So let's expand his scale so that our scale matches the measurement of the building, which is 1.83 millirads. And this is our scale. This is more correct. It's still not accurate, but it's much more correct than what he put in his video. So you see here, we've got roughly 1, 2, 3, almost 4 notches on that scale, which is equal to 1.83 millirads. Right, and the problem there is, of course, is the base of the mountain is way, way down here, off the screen. And if we live on a plane, a flat plane, then something that's 188 kilometers away, the base of that on a flat plane has to appear much higher in your field of view than something closer. So that basically contradicts the flat Earth, and the only way this base of the mountain can appear lower in your field of view is if the Earth is curved. All right. There's also a way to double check that result in a more accurate way. So there are 3 fairly easily identifiable buildings. Le Méridien is the one we just looked at. Pacific Plaza over here, and the Sea Castle on the beach, and you can see the roller coaster at Santa Monica Pier just in front of it. And all I did is in Google Earth I drew a line from the observer location to each of these buildings and measured the heading. So the heading to Pacific Plaza is 96.14 degrees, and the heading to Sea Castle is 97.84 degrees. So there is 1.70 degrees between Pacific Plaza and Sea Castle. And we can then make a ruler or an arrow to represent that 1.70 degrees on his stitched image. And this is this blue arrow here. But we want to find out, we want to scale that arrow against the height of San Jacinto mountain up here. Right. So it is 188.64 kilometers to the mountain, and it is 3,302 meters high. If you plug that into an angular size calculator, it comes out at 1.00 degrees. And as I said, we want to scale this against the angular distance between Pacific Plaza and Sea Castle, which was 1.70 degrees. So this new arrow that we're going to scale the mountain with needs to be 59% as long as the first arrow. And here it is here. And we can do this as long as this image is not stretched horizontally or vertically. If it was, then the scaling would not work, because what we're about to do is stick it up against the mountain. And as you can see, the base of the mountain is again way, way, way below sea level, much closer. And I hate to repeat myself, but that just cannot happen on a flat Earth. This line here, being below this line here, is indicative of a curve. So, thanks again. Thank you in particular, JTolan Media, for proving the globe.